All right, so now let's go through this example where we have two batteries connected with a resistor network, and we're going to use Kirchhoff's rules to evaluate the power dissipated in the 8 ohm resistor over here. All right. So the first thing we should do is, again, make sure we're explicit about our goal. Our goal is to calculate the power that is dissipated. All right, so we're going to be calculating the power through this resistor. So likely, for power in a circuit, we're going to make use of our power formula. Power is the current times the voltage drop across the element we're interested in. And that means that we're going to have to need to find the current through R3, as well as the voltage drop across that resistor. All right? Now, before we just jump in and start plugging away, it's really a good idea to take a look at the circuit and think about what you might do, and then kind of plan ahead and then go out what you might do after that. In other words, it's a good idea to make a mental plan before we just jump into the problem. So let's do a quick review. If this were a simple circuit, then we could do it by the methods we've used previously. We could just reduce this down by series and parallel combinations until we get to a single battery and a single resistor. But we can see here that with two batteries in the circuit, that's not going to be a straightforward effort. So that points us to the idea that we should probably use Kirchhoff's rules and evaluate this as a system of equations that we need to solve. All right, so let's take a look at this. If we look here, we can see that these two resistors are actually in series, right? I even made it very obvious by labeling them as resistor 2A and resistor 2B. Again, the criteria for saying that two things are in series is that if you pass through one element, then you have to pass through the other. There's no junction points in between the two. And that's certainly the case for this set of resistors. We can also take a look at over here and see that these two resistors are in series as well, right? Because if you pass through this resistor, then you have no choice but to pass through this resistor because there's no junction points in between. Good. So since we can simplify the circuit down a little bit, it is in our best interest to do that before we start writing out systems of equations, because then we will only have 1, 2, 3 resistors to deal with, as opposed to 5, which means that we would only need 3 currents to deal with, and 3 unknowns would require 3 equations. And so that's a much simpler analysis. Okay, so our first step is to use the idea of finding out an equivalent resistance to simplify the circuit as much as possible. We'll start by taking these two in series, as we said just a moment ago, and we'll write that out as R2 is equal to R2A plus R2B is equal to 4.0 ohms plus 2.0 ohms is equal to 6.0 ohms. All right. Then we can take a look over here at this pair and say we can combine those two in series, and that will give us R1 is equal to R1A plus R1B is equal to, in this case, 1.0 ohms plus 3.0 ohms is equal to 4 ohms. All right, and so we replace the two resistors in series with this single resistor, and we replace the other two resistors that were in series with this single resistor, and we now have a much more simplified circuit. But at this point, we really cannot simplify this down any further using just equivalent resistances. You can see that these R3 is really not in series with either R1 or R2, because you go through, if you take pass through R3, you get to this point and you have a choice as to which one to go through. You can also see that we can't easily, using the rules we know, put any of these resistors in parallel, because R2 here, the top of R2, although it's connected by just plain wires to both the top of R3 and the top of R1, the bottoms of R2, R1, and R3 are not connected by simple wires. There's a battery that's in between when you're trying to go between any of those points. So we cannot connect these by a simple series or parallel connection. So we are now going to resort to using Kirchhoff's rules. And the first step in using Kirchhoff's rules is to pick a direction for each current and draw it in, right? Now we've got 3 currents because we have 3 resistors. So we're going to want to draw an I1 that goes through resistor 1, and I'll draw it this way. And we're going to need an I2 that goes through resistor 2, and I'll draw it this way. And we're going to need an I3 that passes through resistor 3, and we'll draw it this way. Now again, you might ask, how did I know to draw these currents in these directions? I didn't. You simply choose one. These are proposed currents. It may turn out that we chose all the right directions, or it may turn out that we chose one or more of them wrong, but that will show up as a minus sign at the end of our calculation. So we'll just propose that the currents run in this direction, and we'll work with that. The next thing we need to do is to write out the Kirchhoff junction rule for either point A or point B. So let's choose point A here. Let's look up here, because this is where we drew our currents. And from this, the idea that the sum of the currents in to a junction has to equal the sum of the currents out of the junction gives us the relationship that I1 plus I2 is equal to I3. And we'll hold on to that particular equation for later. The next thing we're going to do is we're going to draw 2 Kirchhoff loops. Remember that in this case we're going to have 3 to choose from, but since we already have one relationship between the currents, we really only need to use 2 of them, because we have 3 unknowns, I1, I2, and I3, and we need 3 equations. Here's equation number 1. Now we generate 2 loops to give us equations number 2 and 3. Since we are trying to calculate the power through R3, it makes sense that we might want to choose some equations that have R3 in it. So we're going to choose 2 loops that both pass through R3. This is not necessarily a hard and fast rule, but in a general good practice. So we will draw a loop that runs in this direction, and we'll call that loop alpha. And then we realize that there's a second loop that will pass through R3, and that is maybe the one we can start here at point B and go all the way around here, pass through EMF1, pass through R1, pass through R3, and come back. And we will call this larger loop beta. All right, so let's clean up the diagram a little bit. We've got our 3 currents, we've got our 2 loops, and now what we're going to do is we're going to write out Kirchhoff's loop rule for the smaller alpha loop. All right, so we'll just go ahead and proceed. The sum across the loop of all the voltage changes has to sum to 0. That is Kirchhoff's loop sum rule. And explicitly here, that loop will then include the voltage change across EMF2 here, the voltage change across resistor 2 right here, and the voltage change across resistor 3 right here as we go around this loop. The next thing we have to do is we have to take a look at the sign of each of these terms. Now for the battery, we note that the loop is running from the negative to the positive terminal as we follow the loop, and that is the normal direction that we use for when we consider a battery. And so that will come in as a positive voltage change, so we'll write that as plus EMF 2. The next thing to note is that the loop runs in the same direction through these resistors as the proposed currents through each of these resistors. This one goes up, and this one comes around here and goes down through R3. So we're going to use the convention that in the normal orientation, we have a voltage drop across resistors, and that voltage drop from Ohm's law is going to be I2 R2 for across R2 and minus I3 R3 for resistor 3. Now ideally we would rewrite this equation purely in terms of symbols, leaving all the R's as just R's and leaving the EMFs as just EMFs and solving for a relationship between I2 and I3. But I know for many of you it is easier to see what's given if we actually put in some numbers, so let's go ahead and do that at this point. We'll go ahead and write that 4 volts for the EMF2 here is equal to I2 times 6 ohms plus I3 times 8 ohms. Right. And all we've done here is, because all of this is equal to 0, we can bring this term and this term over to the other side and set them to be positive and equal to EMF2, okay, which was 4 volts. So now we can do a little bit of algebra on this, and we'll isolate for I2. Let's say I2, we'll make that times 6 ohms, is equal to the 4 volts minus I3 times the 8 ohms. And the reason we're doing this is because we'd like to have a relationship between the currents. So we're going to try and get I2 in terms of I3. All right, then we divide both sides by the 6 ohms, and we get I2 is equal to 4 volts over 6 ohms minus I3 times 8 ohms over 6 ohms, which, plugging into a calculator, gives us that I2 is equal to 0.66 amperes, because volts over ohms will give us a current, minus 1.33 times I3. And that is our relationship between I2 and I3, or at least one more relationship between I2 and I3. All right, so we'll save that relationship. And now it's time to write off Kirchhoff's loop rule for the larger loop, beta. All right, so let's just go ahead and again write out the sum over the loop of all the voltage changes has to equal to 0, which in this case, for the beta loop, we're going to go this way through EMF1. So that's going to be a voltage change across EMF1 plus a voltage change as we pass through R1 plus the voltage change that we get. Right? We are following along this path here, so we've gone through R1, we go up through here, we end up going through R3, and then we get back to our starting point. So we add the voltage drop through R3. And again, looking at the direction of the loop as we go through the EMF, we're going from minus to positive, so that's our normal direction. So that's going to come in with a positive sign. So positive EMF1. But then we look and we see that we are going again through the resistor R1 in the same direction as the proposed current. Right? The current runs this direction, and that is the same direction as the loop, so that we get our normal voltage drop across the resistor. So we'll write that as I1 R1. And then we look over here at R3. The current running through R3 is running in the same direction as the beta loop. So that also comes in with our normal sign of minus I3 R3 for the voltage drop across the resistor. So plugging in numbers, we get 12 volts for the EMF is equal to I1 times the 4 ohms for that resistor plus I3 times the 8 ohms for that resistor. Okay, so there we go. Again, what we've done is we've taken the I1R1 and I3R3, moved them to the other side so that we could come in with a positive sign. And again, what we're shooting for is to get a relationship between the currents. So what we're going to do is we're going to pull one of the currents out front. I'll choose I1. It really doesn't matter which we choose. We'll still be able to solve the system of equations. But I'm going to choose to pull the I1 out front so that we can get I1 in terms of I3. Right, so we're going to have I1 times our 4 ohms is equal to 12 volts minus I3 times the 8 ohms, where I've just taken this term and pulled it to the other side with the minus sign. All right. Dividing both sides by 4 ohms, we get I1 is equal to 12 volts divided by 4 ohms minus I3 times 8 ohms over 4 ohms. So that we finally get I1 is equal to 12 volts over 4 ohms is going to be 3.0 amps minus 8 divided by 4 gives us 2, so we have 2.0 times I3. And that is our third relationship between the currents. All right, so let's clean that up a little bit and move on to our next step. Our next step is then to combine all three of these equations by substitution so that we can solve for I3, because you'll remember that the goal here is to find the power through that resistor. And now you can kind of see the logic for why I solved previously I2 in terms of I3, and I solved previously I1 in terms of I3, because then what I can do is I can start by bringing down my conservation of charge law and write I1 plus I2 is equal to I3. But then I can substitute this equation in for I1, and I can substitute this equation in for I2, and I1 can then be written in terms of I3 here, and I2 can be written in terms of I3. And so I will have all three terms in terms of I3, which means I can solve for I3, which is what I need to solve the power dissipated through R3. All right, so let's do it. We'll take this expression and we will start substituting in these other equations. For I1, we simply write 3.0 amperes minus 2 times I3. Then we're going to add I2, and there we're going to use this expression right here. All right, so we say that's plus 0.66 amperes minus 1.33 I3. And that's all equal to I3, because we're just finishing up this relationship. All right? So now let's do the algebra. We're going to collect all of the I3s and bring them over to the left-hand side. So we have I3, that's this guy right here, plus 2.0 I3, that is this guy right here, because I've brought him over to the other side, he becomes positive, plus 1.33 times I3. And that's this guy, also positive now because I've brought him over to the other side. And that's all going to equal to what's left on the side over here is 3 amps and 0.66 amps. Right, so we have 3.0 amps plus 0.66 amps. So in the end, we have 4.33 times I3, right? That's 1 plus 2 plus 1.33 is equal to 3.66 amps. And finally, solving just for I3, we get I3 is equal to 3.66 divided by 4.33. If you pull out a calculator, that will give you 0.845 amperes. And there we go. That is our I3, the current through resistor number 3. Finally, we remember that our ultimate goal was to get the power dissipated through resistor R3. Okay, so let's go ahead and apply the dissipated power formula, right? Always write that as P is equal to I times delta V. Specifically, we're going to want the power through resistor 3 is equal to the current through resistor 3 times the voltage drop across the resistor 3. And we realize we already have I3, we just calculated it a moment ago, which means we just need to figure out what the voltage is across resistor R3. And for that, we can use Ohm's law. So we write delta V R3 is just going to be the current through I3 times the value of resistor 3. And we already have I3 again, and we know R3. So this is equal to 0.845 amps from above. And the stated fact that resistor 3 is 8 ohms. And that gives us a final value of the voltage drop across R3 is equal to 6.76 volts, which means we can now calculate power through R3. The power dissipated through R3 is 0.845 amps times 6.76 volts. And that gives us that the power through resistor 3 is 5.7 watts. That's our final answer. But we can take one last step and verify that the currents I1, I2, and I3 actually point in the direction that we initially guessed. It's not necessary for what was being asked, but it's instructive to go ahead and take a look. As we already know, I3 is equal to, and we'll be explicit here, positive 0.845 amps because we calculated that a moment ago. That means because we got a positive value, we guessed correctly the direction. Right, let's now do I1 because we have I1 in terms of I3 by an equation here. So that's going to give us 3.0 amps minus 2.0 amps times I3, which is 0.845. And that's going to give us positive 1.31 amps. So that means we also got the direction of that one correct. Now let's look at our last current, which is I2. And we see that I2 from this relationship is equal to 0.66 amperes minus 1.33 times I3, but we have I3 as 0.845 amps. And that gives us, when we plug that in, minus 0.464 amperes. And this is negative. So it turns out that I2 actually runs in the opposite direction that we guessed. It runs downward through resistor 2 instead of upward. In other words, the current coming from EMF 1 splits into I2 and I3 at point A. Nonetheless, our calculations and all our answers are correct as long as we remember that the negative answer for the current on I2 just means that it runs in the opposite direction that we initially drew. So we can just finish it up by correcting that diagram to make the currents run in what we now know to be the proper direction, and then list all the currents as positive numbers. And that's it.